Hi everyone, welcome to my channel. So today we're going to solve a very easy linked list problem, reverse the linked list. So basically what you need to do is that we're given the head of a singly linked list and we need to reverse the linked list and then we need to return the new head. So in each list node, it stores the data, which is an integer, and it also stores the pointer that points to the next list node. And the property of the single linked list is that the last list node should point to none in Python. So how do we go about reversing a linked list? So the first option is a stack-based option. So intuitively, we can use stack to reverse the order of a list. So basically, what we can do is that we can scan the linked list from the head to tail, and we can push the elements onto the top of the stack iteratively. And after we scan the linked list, we can just go back to the stack and we can pop the items from the stack. So stack has a very important property called last in, first out. So basically the last element that you push onto top of the stack will be popped first. So in this way, if we're popping the elements from the stack, we're effectively reversing the order in which we scan this data. So without further ado, let's just code this up. So the first step, we need to scan the linked list. So what we need to do is that we need to have a current pointer starting with the head of the linked list. And while this is not the none pointer, we need to move the current pointer to the next one. So this while loop will execute until it reaches the end, until it reaches the null pointer. So when we're scanning the linked list, we need to push it into a stack. And in Python, basically it's a list. The list, we can use a list to mimic the behavior of a stack. Basically a list. So every time we visit a node that is not empty, we can just push it to the top of the stack. The top of the stack is just basically the end of the list. So basically we need to append that to the stack. And this is the scanning phase, and then we need to pop elements from the stack until the stack is empty. So what we could do is that we can use another while loop. So while stack is not empty, we can do popped item is basically stack.pop. So basically in the list, it will just give us the first element from the it will give me the first element of the list, which is not the first element, the last element of the list, which is the end of the list, which is the top of stack. And what we also need to do is that we need to reorganize these list nodes such that in the end we can return the head. So what we should be doing is that we should look at the first node that is popped. So that should represent the head of the new list. However, we don't want to write additional code to handle the first node. So what we could do is to use a dummy node. So use a dummy node that precedes the head. So a dummy node is often used in linked list related problems. So basically a dummy node is a list node that precedes the head, and we give it a value that doesn't mean anything, and its next pointer will point to none. And then we can set the current pointer to be the dummy node, And every time we pop a new list node from the stack, we can point the next pointer of the current node to be the popped item, the popped list node from the stack. And after that, we'll need to move the current node to the next position. And so basically, this while loop runs when the stack is non-empty. So when the stack is empty, we will have we would have all of the list nodes. We would have processed all of the list nodes. The only thing that we need to do is that we need to set the next pointer of the last list node to null, because otherwise it will be like a circular linked list. So this is important. We need to set current next to be null, and in the end, we can do is that we can return the next pointer of the dummy node. So basically, the dummy node is very useful here because it is the node that precedes the head. So basically, dummy.next is always the head, and it also works when the linked list is empty, because in that case, dummy.next will be empty, and then it will also be the head. So let's just see whether this works. Okay, there's a typo here, so it should be next. Okay, it looks like the running time is all right. The memory is not so good. So which brings us to the complexity analysis. The time complexity here is big O(n), because we're basically scanning the data twice. The first time is when we're scanning the linked list, and the second time is when we're popping the elements from the stack. And the space complexity here is also big O(n), which is not optimal. This is because we're using an additional stack to store all of the list nodes. So in the second part of the video, we're going to talk about how we could devise a new algorithm such that the space complexity can be reduced from big O(n) to big O(1). So next, we'll discuss how to implement a solution in a memory efficient way. So if we cannot use a stack to temporarily store the list nodes so that we can pop them in reverse order, we'll need to basically manipulate, and basically we need to change the pointers of the list nodes. So the idea is that we need to treat the start of the old linked list as the end of the new linked list, because we're only given the head of the old list, so we can only traverse in this order. And also, because we need to reverse the pointers in the end, so for each node, as we visit them, it would be nice if we have access to the previous node, because eventually we want to reverse the pointer's directions. So basically, for 1, we want to set its next pointer pointing towards null, and for 2, we need to set its next pointer, instead of pointing to 3, we need to set it pointing to 1. But we also want to process these list nodes in the original order. So what we do is that we can use a for each node pointed by the current pointer, we can compute the next position of the current pointer in the original linked list. And so initially the prev pointer is pointing towards none, and the current pointer is starting with the head pointer, and the current next pointer is pointing towards the next node from the current pointer. And in the first iteration, we need to set the next pointer of the current pointer to its previous node. So in this way, this is the most important step of this algorithm, because in this way, we're reversing the direction of the pointers. And Then, because we need to move on to the next node in the original linked list, we need to move current pointer to the current next. So luckily we stored the current next position in the original linked list. And before we update the current pointer, we need to set previous pointer to current pointer. So in this way, every time we're visiting a new current node, we will have access to the previous node in the linked list. So basically, cur is moved to cur next, and prev is moved to cur. So we repeat this process until the current node is pointing towards none. So in the end, in the last iteration, the current pointer points to none, and the previous pointer points to the last element of the old linked list. And because we're reversing the linked list, the last element of the old linked list will just be the first element of the new linked list. So basically, prev is now the new head. So we can just set head to be prev and return head, or you can just return prev as the new head. So here we're gonna go through the implementation. So initially, prev is set to be none, and cur is set to be the head of the current linked list. And we need a while loop to visit all of the list nodes in the original linked list. So most of the times we're doing something like this, and the reason why we cannot do this is because in between here we need to set current.next to be the previous node, and we also need to set priv to be the current node. And because we have changed the value of current.next, so this current.next here is no longer pointing towards the next position in the original linked list. So we need to store that old position using a variable like current next. So basically, before we update that, we need to store that in a variable, and in the end, we can just reuse this variable to make it move along the old linked list. And in the end, we can just return prev, because prev will be at the end of the old linked list, which is the at the beginning of the new linked list. So we're just going to submit it and see how it works. So as we can see that the efficiency is similar to the previous stack-based approach, but now the memory is improving by a lot, because now the time complexity is still linear. However, the space complexity is now reduced to constant, because we only need some variables to store the previous node, the next node, and the current node, and that will be a constant time complexity. So that's pretty much it, and thank you for watching this video, and see you next time.